Welcome back. So today I want to spend a little bit of time talking about, well, two new operators, or two new classes of operators. And these are mentioned in your textbook, and I just want to kind of put them in my words because I think these operators are extremely useful once we put them in the language of linear algebra that we're kind of used to. So the two operators specifically that we're going to be looking at are operators called outer products and projections. And they're really related to each other. In fact, one is part of another one. But let's start at the beginning and develop some intuition for what these things might mean. So you remember that I have a general state, right? I say this all the time. I have some state, psi, and I'm going to decompose that state onto a set of basis vectors. Now, some operator, right, defined these basis vectors. It could be a Stern-Galick experiment, it could be a spectroscopy experiment, it could be something that defined these eigenstates. Here I'm going to simply say, at least for the moment, that there are just two of these eigenstates, phi1 and phi2, and therefore I have two probability amplitudes, one corresponding to the probability amplitude for state 1 and one corresponding beta corresponding to the probability amplitude for state 2. Now, we've gone over a lot what it means to calculate or try to extract alpha or beta from this state, right? If I want to get one of those expansion coefficients, I have to use the Fourier trick, right? And so what does that mean? Well, in this case, if I want to get alpha, it means taking the inner product with the state that I'm interested in this case that's phi1, so I'm going to multiply this through on every term. And then I take advantage, of course, of the orthogonality of my system, and I take advantage of the normality of my system, right? That is that the inner product of phi1 with phi1 is equal to 1, and I get that alpha is the inner product of phi1 with psi. And this is what I think about when I have that idea of a probability amplitude, right? We use this word project or decompose, right? I do the Fourier trick to get out what that probability amplitude is by taking the inner product with the state that I'm interested in for each of the states that I'm interested in. Well, what we haven't really done yet is kind of play with that backwards, right? And take that definition of alpha and beta as, decompositions of inner products and plug them back into my state, right? And now it's a little funny to see it this way because we obviously don't have, there's no more alpha and beta in here because I've replaced them with the inner product of phi1 with psi. But this is okay, right? I mean, it's exactly the same thing I had in the previous slide, except now it just seems to have more terms. But I do want to remind us that this thing and this thing, these inner products, are just scalars. I have them in front of the state just because that's the way I had them before, but there's no reason not to move them after the state. And when I move them after the state, or if I take the state and move it to the left, I end up with an expression that starts to look, well, actually kind of neat, right? I have something that looks like a ket phi1 with a bra phi1 and then my state, and a ket phi2 with a bra phi2 and then a state, right? And so I've now defined by doing this. Now I can take my state out. I can eliminate it from this thing, and I get this beautiful thing that I've written in brackets here. And if you look at this thing in brackets, you say, those are not inner products, right? Each of those two terms, or I should say neither of those terms is a scalar. This thing in the hard brackets is not a number. It's not an inner product. In fact, it's a matrix, right? Because if I take a column vector and I multiply it by a row vector, I actually end up with a matrix. But what's fun is if I now take the left-hand side and propagate it all the way down, I know exactly what matrix this must be, right? It must be the identity matrix, because this combination of all of these outer products takes my original state psi and returns my original state psi, right? It has to be the identity. The identity is the only thing that can do that. And so in doing this little bit of algebra, I've done two things. First, I've defined an outer product, right? Which is one of these terms, and it's exactly the opposite of an inner product, right? An inner product takes two vectors and gives you a scalar, takes two things and gives you something simpler. An outer product is the other way. It takes two things and gives you a matrix, right? It gives you out an operator. And if I sum all of those outer products together, then I end up with the identity matrix. And so we're going to now I'm going to write it generally. So now I don't know, perhaps how many eigenstates I have, but I have a set of eigenstates. I'm going to label them by I. I actually have one outer product, again, opposite of the inner product, corresponding to each one of the eigenstates of the system, right? So I can define that for any eigenstate. And when I dig into this, I found, which we just saw, that the sum over all of those outer products has to be the identity, right, via that proof that I just had. But if I take just one of those outer products, well, that's really a projection, right? So let's do an example. So why is that one term a projection? Well, let's go back to a two-state system, actually spin up and spin down. I have 3/5 up plus 4/5 down, right? And I think that's normalized. I'm going to take one of these outer products, the outer product corresponding to the spin up state, and I'm going to act that outer product onto my psi. And I can see on the right-hand side, that means acting the outer product onto the 3/5 up plus the 4/5 down. Let me switch colors here. But I know if I now take the inner product of this term with this, well, they're orthogonal. That's going to be 0. And if I take the inner product of this again with the first term, well, I get 1, right? And so what do I end up with? I end up with plus times 3/5, right? So I've taken out the part of the state that corresponds to the plus. Now, why is this a projection operator instead of just a projection? Or why am I calling this a projection operator instead of the Fourier trick? Because the thing that I get out is a vector, right? Because these outer products are matrices. The outer products are operators, and therefore they take in one state, they push out one state. And so this projects it, but it kind of keeps the unit vector, right? It keeps the eigenvector in that direction, so that way the thing that I end up with is still a vector. It's not a good vector, right? And this is important. It's not normal. This is the thing that comes out of this is not a normalized eigenstate, right? It's proportional to an eigenstate, but it is not a normalized vector, right? Well, okay, there are probably some exceptions. If I were to put a pure state in, I project it onto a pure state, then I probably could end up with a. In general, you are not guaranteed to get out a normalized state. Okay, and so I'm going to just remind us that this thing that we want to do here, not normal, right? Not a normal thing to do. Okay. So why your textbook goes sort of one step further and says we could take this and then add a normalization factor to it and call it the measurement operator. I have to say that's language that I'm not really used to, so I'm not going to use it in this video. But if you wanted to take this projection and have this state come out of this projection operator, you could then normalize the state to create a pure state, right? You could then normalize the state and return yourself to an eigenstate of the whatever operator it is you're using. Of course, I probably would have used the language that when you made that measurement, you collapsed the wave function into the pure eigenstate rather than. But I didn't write the book. But it's okay. I mean, you get the point here, right? That these projection operators are they are operators. They take in a state, they output a state, but the state that you get out is not a good normalized state that you might want to do quantum mechanics with afterwards. Okay, so take-home messages. First, outer products are operators. We get matrices out of them. We get something more complicated than vectors, something that is really an operator. And it's often useful to remind ourselves that I can always take the identity matrix and rewrite it as a sum over all of the outer products. This might not seem like it's totally useful now, okay, but I promise you in maybe 2 or 3 or 4 or 7 or 10 weeks time, I'm going to ask you to do some proof of something, and remembering that the identity matrix can always insert an entire copy of eigenstates is something that's really going to be useful to us. And so having something that's equal to the identity that also contains all of my eigenstates is something that's pretty cool. And last but not least, I can define a set of projection operators that output states that tell me how much of my vector is in some direction times that direction, right? So I can get a vector out that projects using just a single one of these outer products. Okay? Have a great day.